Okay, here we go. Hello and welcome to our presentation. My name is Michael Schröder. I'm an IT architect. I'm a VMware certified instructor and blogger. And before my IT career, which started more than 50 years ago, I used to be a biologist at the University of Heidelberg. So today I'm basically coming back to my roots, which is nice. And with me is my co-host, Lars Fiechtner. Hello, Lars.
Hey, Michael, thanks for the introduction. So let me introduce myself. My name is Lars Fiechtner. I'm a technical account manager working for the VMware Professional Service Organization based in Germany. So I'm looking more or less to the automotive companies in our country. Besides that, I'm working a little bit also on the topic SAP HANA virtualization on VMware. So if you don't saw the latest press release from Runecast, so please check it out. There's new exciting features in it from Runecast, so you will love it. So with that, thanks for joining. Thanks for Runecast for the opportunity about this virtual conference, this first Runecast virtual conference. And the reason is why we do a virtual conference, Michael. Huh? That's the question. The question is, and I think you're all aware and you all are affected, and you mainly all of you sitting at home, yeah. So the challenge that we have today globally, and it's not specific to a part of the world, is the coronavirus and the COVID-19 disease. So what's happened? It's happened, the countries shutting down by their governments. They force you to stay at home. More or less, it depends in which country you are. You have to ensure that you have a physical distancing. Of course, some of you are saying it's social distancing. I'm not a friend of this topic regarding we're trying to be physical distancing and not social distancing, and therefore it's a very cool opportunity to speak with you, Michael, on this virtual conference. In the V community, what is really the passion of this social community that we established over the couple of years. So, but what's happened? So let's see, next slide, please. So a lot of people are talking coronavirus, a lot of people is talking about COVID-19, and a lot of people saying SARS-CoV-2. And this also includes myself, was a little bit challenging what this means exactly. So I think hopefully you can remember the time we have the SARS virus was around 2002, the coming up of SARS virus. And the coronavirus, it's the reason for that is called SARS coronavirus 2, regarding the has a dependency on the first SARS coronavirus, what we saw in 2002 until more or less 2004. So that's the reason why you see in some press releases, in some documentation, if you follow by Twitter or looking in the TV, you saw a lot of people talking about SARS-CoV-2. But this is the virus. On the other hand, you have the disease. So if you're affected and your human cells has an issue and you get fiber and you maybe have really issues with your body, this is the disease called COVID-19. COVID-19 means the coronavirus disease 2019. 2019 regarding was the first time the virus or the disease coming up. Maybe you remember that in a big Chinese town called Wuhan. So it was mid-end of December. That's the reason why it's called now COVID-19. So one is the virus, one is the disease you get affected if you have the virus in your into your body, in your cells. And why is this the challenge today? It's regarding 20% of all people that are affected by the coronavirus and they have the COVID-19 disease needs a hospital treatment. 20%. It's a huge number if you compare that to your village, to your town, to your country. So that's the reason why everybody talking about flooding the curve. Yeah, so trying to be the people that have to stay in the hospital to the same time has the lowest number as possible. And more or less 5% of this 20% needs intensive care. That's the reason different countries has a different amount of care capacity. So that's really the challenge that all our medical system are fighting against today. And currently there's no vaccine or cure. So that's exactly the point, is that you get affected, your body has to fix it by yourself, maybe a little bit help of intensive care. But at the moment, there is no solution. There is nothing what you can do in advance to avoid this. That's the reason why we trying to get to stay at home. That's the reason why we trying to get physical distances to avoid to get affected by the virus and getting the COVID-19 disease. So a little bit, this the coronavirus. To be honest, if I look much more to this virus, it looks at this point looks not bad. Yeah, it's a nice color, but you will learn that is not there is no fun on that. There is no execution on that. But we have to understand how this virus works and looks like from their proteins, for example. And what the biologics and the scientists is doing is to find a solution of existing drugs. That means we have some drugs in the past for malaria, for Ebola, and so on. And all these people trying to understood how the virus is working from their proteins, how they connect to the human cells, and what existing drugs can help to avoid to get affected, or if you're affected, how they can, make you recover, or how you get recovered. And one model is to protein folding. And what is protein folding? And as I have Michael with me, so as he was the PhD at the University of Heidelberg, I think, Michael, I think you're the right person to explain a little bit what this means exactly.
Okay, I'll do my best. So what is protein folding? Well, we all know how to fold a sheet of paper or a blanket, for example. But how can you fold a protein, and why is that so interesting for research? To understand protein folding, we first have to talk a little bit about proteins in general. Let me give you a brief introduction. But by the way, I need to say that this primer is very simplified. So if you're an expert in biochemistry, please be patient. This is not going to be a science lecture. A protein is a big molecule that consists of a long chain of amino acids. And you can see it in the picture on the left. And these amino acids are the building blocks. They form a long chain like pearls on a string. And that's what we call primary structure, and it's well known. So if you know the sequence of the amino acids, so you know the protein. But the protein isn't usually in a linear form like we see it on the left. There are 20 kinds of amino acids, and they all have different chemical properties. And depending on the sequence, amino acids tend to clutch together towards each other. And they can form little structures like spirals, or we call it helices. And you can see it, it looks like a macaroni on the upper part of the middle picture. Other amino acid sequences will form sheets, flat sheets. And you can imagine a rope put on the ground and you fold it back and forth and back and forth, and you get like a sheet-like structure. And that's what we call the secondary structure. And this is easy to predict because we know the properties of each amino acid and how it does behave. But the tough part is to find out how these spirals and these sheets organize themselves in 3 dimensions, how they organize to the final protein. And that's what we call the tertiary structure. And it's quite tricky to find out how it actually looks like, because we can't use a camera and just take a picture of it. It's too small. And scientists will make crystals of the protein, and then they fire X-rays on it, and in a result they get a very strange image. And from that image you can calculate how it actually looks like in 3 dimensions. But it is only a snapshot, a point in time, like a still image. So basically we are coming from a random coil here on the left, and we're going to a complex 3-dimensional structure. And that happens all the time in every living organism. And it's pretty normal, because a protein needs to fold to become active. But why is that so important to know? Why is it so important to know the 3-dimensional structure of a protein? Thinking about enzymes, for example. Enzymes are special proteins, and they aren't static, they're moving, they have flexible parts, and they act like nanomachines. Some of them can pump ions, others can work like a pair of scissors, others will glue molecules together, or they can even function as a gatekeeper to open or close a channel through a membrane or a cell. So with classic methods, you only get one picture, one moment in time, but you cannot see it in motion. And to understand an enzyme, it's important to see it working. How does it move? And to give you a real-life example, imagine you have never seen an excavator in your whole life. And then somebody shows you a picture of an excavator. Will you understand how it works? Well, maybe, or maybe not. But if you're watching a video of an excavator in action, you will quickly understand how it works without ever having seen one. And that's the same with enzymes.
But Michael, this is very interesting, but this is not easy really to understood that topic. I think that's not that easy part. But we talk about a lot of things about protein. But what is this in cases of the virus and the COVID-19 disease?
Okay, yeah, let's come back to the virus. On the left-hand side, you can see a model of a new coronavirus, and you can see there are red spikes on its surface. And these red spikes are responsible for the docking procedure to a human cell. And the docking procedure enables the virus to enter the cell for a hostile takeover. So if we could find a drug that intercepts this docking procedure, then we can prevent the virus from entering the cell, and we can prevent the virus from reproducing, and we can prevent the virus from infecting the person. And hooray, we found a cure. The problem is that this docking site is hidden. It's inside the protein. And we see a model in the middle picture. And this is actually the top of the spike already connected to a human cell. And you can see the human cell. Let me point this with a laser pointer. Hold on. And you can see the human protein is here in purple. And just below, there is the docking site of the virus. And the problem is that this site, most of the time, is hidden. And you can't attack something that is hidden. So we need to find out how this structure looks like and how it behaves. And that's where simulation comes into play. So we can't watch it, we can't shoot a picture while it is infecting a cell, but we can simulate how it is working right in a moment when it is about to infect a cell. And the question is, can we calculate the 3-dimensional structure? Well, yes, kind of. It's not an equation. It's not like you put some parameters in and 2 minutes later you get a result. No, that's not it. It's more like gambling. So we have a sophisticated algorithm that is twisting and turning the whole molecule and checks which position is possible and which is not. And it takes a whole lot of iterations and do it again and again. And you can see it on a picture. We start on the left with a linear structure, a coil, and then we gamble. And in the end, you get a couple of structures that resemble the life state in 3 dimensions of the protein. And think of it like a stop motion movie. You have a couple of pictures, and the pictures put together, they will get you the motion that happens. And the problem is, the bigger the molecule, the more iterations you will need. And it's just crazy, because with more atoms and more parts of the molecule, it doesn't go linear, it goes exponential. And so we will need a hell lot of compute power to fix that. And by the way, Lars, what is the most powerful supercomputer we can get today?
If you can get it. So
if you can get it.
If you can it. The most powerful supercomputer is at the moment the Summit supercomputer. It's made by IBM in 2018. It's located in the Oak Ridge National Lab. It's in Tennessee, US, and has more than 4,600 IBM Open Power 9 systems. And each of the systems has 2 Power 9 CPUs. But what's very interesting is every of that has 6 NVIDIA Tesla V100 GPU cards. And as you know, GPUs are very, very beneficial to run calculation, simulation, and so on. That's exactly what you described in the last slides. And this supercomputer has 122 petaflops, what is a lot of compute power, but consuming 13 megawatts of power consumption. That's not that less. Yeah, but this is number 1 in the world from a top 500 supercomputer list perspective.
So would you say that a supercomputer is the best way to calculate protein 3D structures?
The challenge of these supercomputers is all of the supercomputers has a reason, and somebody is owning the supercomputers. In this case, this lab is owning the supercomputers, and a lot of supercomputers in the world are sponsored by the industry, and all of these companies has their interest and their agenda to do it. And on these supercomputers, you have specific slot times where you can rent compute power. You maybe have to pay it or you get it regarding your non-profit organization, but you're fighting against other projects. This could be projects by the government, this could be projects by the military, there's also projects by the NASA and so on. So it's a really, really challenging part. And of course, this kind of supercomputers are made for calculation at the same time. And this is not easy and needs a lot of investment to maintain this kind of installation.
So what's the alternative then?
The alternative is distributed computing. Distributed computing means you put a couple of computers over the globe together, a little bit different to supercomputers. They are independent. What it means is you create a work unit, you send a work unit to the distributed computer. This can calculate and sends only the results back. This doesn't mean, compared to supercomputers, you need a very fast network between all the nodes. So you can really have distributing computer over the globe. So it doesn't matter if you have one device in the West Coast, in the East Coast, in Europe, in Asia. Doesn't matter regarding, you doesn't need so rely on latency. You send a package, they will calculate and they come back in with the result. And what makes this very nice is you can scale. So every PC, and there's 1.5 billion of computers out of the market, you can add to this distributed computing, and you contribute to this structure of computer together. So you can do global distribution. The nice thing is you can tolerate failures. Doesn't matter. You send a working package, it doesn't get an answer. You take this working package, send it to another computer. They can calculate, can send the results back, and they have a common goal, for example.
Okay. In the last few weeks, we heard a lot about a project called Folding at Home. Can you tell us more about it?
Of course, folding at home, and this is very, very, if you go to the medias like Twitter, a lot of people are tweeting about folding at home. But folding at home is not something is coming up from yesterday. So folding at home was founded or introduced in mid of 2000 by the University of Stanford in California. And what they're doing is they support different non-profit projects by distributed computing. So you get a piece of software. If it's for Windows, Linux, Mac OS, you can install it. Then you can decide in which kind of projects you want to contribute. That doesn't mean this has only one project, this can be other projects. So you can really decide in which way you are supporting that. And they have more than 760 petabyte flops. So if you compare it to the Summit, the #1 supercomputer with 122, now we have a couple of more petaflops to calculate, for example, folding of proteins to fighting against COVID-19. And the good thing on this is a non-profit project. What this means is if you put your compute resources to participating on this project, folding at home, all the results will be contribute to all the scientists and biologists over the globe without to having invest money. So all the results will be given to non-profit organization like a university and so on to work with the results. So that's the point I think we have to mention about Force for Good. So it's a non-profit project. You can contribute, you can participate, but the good thing is the result will also help non-profit organizations.
Oh, that sounds great. What else are they working on?
They're working on a lot of projects, yeah, of course. So they're working on neurological disease. Yeah, so I think that most people are knowing what is Alzheimer's, Huntington, and Parkinson. So they're working really on that parts of pieces, but they're also working against cancer, breast cancer, kidney cancer. There's a special project called P53. But on the other hand, they're working also against virus. And in this case, they're fighting against the COVID-19 disease. So, but the question is, and maybe you can answer this question, Michael. If you participate to the COVID-19 project, is there any results or any outcomes so far during this project?
Actually, yes. Just recently, they published an article, and they simulated the capturing of the corona spike in action. That's the red spike protein I showed in the beginning, and how it works and how it infects the human cell. And thanks to the combined compute power of hundreds of thousands of private computers, Folding at Home was able to simulate this docking procedure. You know, one part of the docking site was hidden inside a protein, and they did a simulation how it opens and how a gap opens and the docking site comes forward. Well, on the left-hand side, you see the fully hidden docking site. That's the normal situation in a virus. And just before the virus is about to infect the human cell, it will open a gap in the protein. We can see it on the right-hand side. And I will highlight it here. If you look at this part, this is on the left is the hidden docking site, and on the right you can see an open gap. And that's the moment when you can attack this docking site with a drug. Maybe a drug that attaches to this docking site and blocks it and makes it unusable. Or you find another drug that will attach somewhere else on the protein and prevents the gap from opening. So what you see on the right couldn't be possible because it can't open, it's blocked. Either way, both methods would mean you have a cure against the disease, and that would be great. So this simulation is just a starter. So going on from here, you can do further research, further simulation. You can try which kind of pharmaceuticals and which kind of drugs fit into the gap and fit into the docking site to block it. And these are just two still images, but on the website of Folding at Home, you find a link to a YouTube video, and then you can see the whole simulation from close to open. It's amazing. And I think that's the subject of further simulations, and there's still a lot of workloads to be calculated. Talking about calculation, by the way, how do we join forces to contribute to the project?
As I mentioned, you can download the software for different operating systems, or like Windows, Linux, Mac OS. You can install it, you can participate on different projects. But on the other hand, what you can do is you can download a pre-imaged appliance by VMware. So VMware has made a decision to build an appliance to running the software into this appliance. We get an approval by Dr. Greg Brownman, Director of Folding at Home, to distribute this kind of software in a VMware appliance based on VMware's Photon OS. So it's easy for you. You can download it. You can deploy the OVA image to your infrastructure. You need only a minimum of 2 vCPUs and 1 GB of RAM. But you can also do this on Fusion or Workstation. Doesn't matter. It's the easiest way. You download it, you deploy it, you contribute, and hopefully you also do some small pieces of work together against COVID-19. So you can go to the fling.vmware.com, looking for the VMware appliances for Folding at Home, downloaded it. What I have to mention is all things are scripted inside the appliance you're doing the deployment. So you will automatically join the VMware team with the VMware team ID 52737. What it means is Folding at Home is doing a little bit of challenging team by team. What it means is this is not you get a #1 place and you get a big prize. So they want really to ensure you that you get the most power, that you unutilized resources to help for example folding of protein. So that's the reason why there's a team ID here. If you look to the screenshot that we had here, you can also have a pull down menu. You get an FAQ document. You get a document how a vGPU or GPU can help more calculation power to the project. So if you have a NVIDIA card in your PC, this will also support it. So and all of that, you can really easily participate. And as there is coming a question from the Q&A panel, from a security perspective, of course, VMware doesn't make the Folding at Home software, and we have to trust the non-profit organization of Folding at Home. But the good thing is if you're running inside of our appliance, you have an encapsulated system, then you can put it in a specific network, a virtual network, so you can a little bit ensure that you're not running in your corporate intranet. You can run it on a DM set or something like that. So with the appliance and the virtual machine, you have more possibilities to ensure the security from that kind of security. You can do it. Yeah.
And am I supposed to run more than one appliance?
Yes, you can install more than one appliance, but during the deployment of the appliance, you have a couple of options. Of course, you can decide, for example, for a proxy, your IP address, and so on, but you can also decide for the deployment type. What it means, you can do small, medium, large, so have different amount of CPUs and memory. So on that, you can scale, or you can deploy more than one of these appliances in your infrastructure to support a project.
So that means if I have a spare test dev cluster with a lot of spare resources, I can put a couple of appliances there and let it calculate and work for the money.
Yes, if you have unutilized resources in your home lab, you have a test cluster in your company, it doesn't matter. You have spare PCs, I don't know, you have I don't know. You can run it where you want. The easiest way is really downloading the appliance. But of course, you have to ensure you do the right things.
You have to ask for permission of your boss.
If you do it in the company or you do it on a cloud service, yeah, you have to ensure anything is compliant and regarding there is. Of course, we are not supporting flings and we are not supporting this appliance. We are thinking the right way is, and this is the policy or the things we had inside of VMware as a force for good. We do something, you can use it, you can run it. We think it's the right way. Of course, if you put it on your highly critical production cluster, please don't do it. Yeah. So that's the only advice I want to give it here. Deploy it, but ensure in which area you will deploy it.
Okay.
But on the other hand, you want to see what you're contributing. For that, the Wavefront team creates some dashboard or one dashboard. And for that, you don't know what Wavefront was acquired by VMware a couple of years back. So there's a UL here in the back, you can execute it and you can see what is the overall team rank of VMware. It's at the moment 97. I think we take the screenshot for 1 or 2 days back. So I think we are good in that. We have more than 1,200 users that are supporting the team. And you can see what is the scores in the last 24 hours, how many worker units what is the overall team rank. It's a nice dashboard to get a little bit an insight in which team, in which project you are contributing. But the same is you can log into foldingathome.org. You can enter the VMware team ID, or you can search for VMware. You get the same data, but not in this nice way. But on the other hand, there are some colleagues out of mine. They created some dashboards for re-robs, for example. Yeah, so if you have an empty screen in your NOC center, you can put this on it to have a little bit a kind of visibility in which kind of way you're contributing. Yeah. So
that's a fun competition for good.
It's force for good. I think. We have to clear. We have all hopefully everybody has a job and we're doing what we have to supposed to do. But on the other hand, during these challenging times, and I'm pretty sure not so many people had this time before. There's a piece where you can give back and force for good. The same what we are doing if you at the moment spending money, the company is doubling that. So that's a kind of giving back to the community, and the same is a little bit going to the closing is that what the Runecast and the team is doing with this virtual conference is it's a kind of giving back. I think this should be in your mind, and this is this passion and the things we are doing in the V community.
Yeah, that's great. So thanks for letting us here showing our presentation, and thanks to Runecast. And so we have nothing to add. Thanks for watching. I think we can stay a little bit in the chat for Q&A. And Do you have the chat open? Are there any questions?
Yeah, there is actually a question in the Q&A section. Michael, can you see it?
Now I can see it, yeah. There's about a security risk, but Lars already answered to it.
Yeah. So hopefully the question is answered. As I mentioned, that of course you download a piece of software. Of course you have to trust the organization where you download it from. I think this is the same if you downloaded a piece of software from VMware or you download it from Runecast, doesn't matter. A kind of trust you have always. While regarding you cannot look into the code itself. Yeah. But with the appliance model, you have really the chance to have an encapsulated system. You can fence it. You can put it in a DMC. You can do it checking what is going in and going out. I think I'm not a security expert, so I cannot make a clarification how big is the risk. Of course, I want to a little bit clarify anything what you do has always a risk. Yeah, doesn't matter if you execute a website in the internet or you're driving a car from here to the supermarket. Yeah, so I think there has to be clear. Everybody of us has to look very clear, but make your own decision.
Yeah.
Hopefully, it's answered the question.
Yeah, you're welcome.
Thanks for the feedback, and the same to Stan.
Yeah.
We have to say thank you for the opportunity to talk about a little bit a non-technical, not infrastructure topic. I think this was also for us, more for me than for Michael, the challenge to dive in the content. But I think sometimes makes sense to have a wider view on the things that are happening at the moment.
Okay, so thank you. Thanks for watching. Bye-bye.
Thanks for joining.
Yeah.
Thanks.
See you soon.
See you.